This is Dan Schneider. On this Dan Schneider video interview, I am speaking about the multiverse with physicist Yasunori Nomura, and the conversation will begin in a moment. This show is about the multiverse, and I'm speaking with a physicist named Yasunori Nomura. And the basic topic will be whether the multiverse exists, if there is a multiverse, how we can test it, and different types of multiverses. So thank you for appearing. And if you could give a little background, 3 or 4 minutes, about yourself, your youth growing up, what drew you to astronomy or to cosmology, and anything that you've written in the field.
Yeah, thanks for introduction. I'm working on particle physics and cosmology and quantum gravity from theoretical point of view. I'm a theoretical physicist. And I got my PhD at the University of Tokyo in 2000. And after that, I was working as a postdoctoral fellow and junior researchers, UC Berkeley, Fermi Lab, Fermi National Laboratory. And now I'm a professor of physics at UC Berkeley. My interest is to focus on fundamental questions like what is space and time really is, and how the universe began, and what that is made out of it. And from these explorations, nowadays we started figuring out that there may be many universes out there, not just our own universe. And I'm thinking if we can test this hypothesis and whether there are further implications of that hypothesis in other areas of physics.
Now, you said that you're a theoretical physicist, and let me open with that, because one of the things that I know that I sometimes think that when I read books on physics, especially popular works, it seems to me that physics over the last 40 or 50 years seems to have gotten away from sort of the scientific principle of actually dealing with things that can be tested by observation. It seems to have gotten more entangled with mathematics, which can be beautiful, but isn't necessarily a representation of reality as we know it. Does it ever trouble you that physics has seemingly gotten detached from observational astronomy?
I kind of disagree with you in a sentence.
Yeah.
Because what is observational or something you can test is really, you shouldn't be narrow-sighted there. For example, when first, how science works is usually you just build your theory by looking at something you can directly test. You theorize gravity by looking at motion of the planets and Newton's apple and so on. And you trust that theory and extrapolate that theory into the regime where you cannot directly test at that moment, or you did not know before, and then see what that theory predicts. And sometimes, of course, that turns out to be a right picture, or sometimes that's not, then you have to extend the theory. And we are still doing completely the same principle. We operate on exactly the same principle. We just have a theory of quantum mechanics. We have a theory of general relativity of Einstein, and we solve these equations, and the multiverse is outcome under certain assumptions and outcome of those equations. And we think about the way you can test that, or you can falsify that, and we just keep thinking. And it's not just like random guess or something. In that sense, it's the same philosophical or basis, or same methodology we are on. And in terms of time scale, yes, it becomes longer and longer to test the theory. For example, like Higgs boson discovered a few years ago, and it took more than 40 years after the theory is born to test that. Yeah, it's becoming slower. The cutting edge physics is like we're really thinking about a very short distance or very early on in a universe, and so it takes a long time, but it's still the same thing.
Yeah. Well, I'm speaking as a layman, and I know, for example, in the last 40-some years, both dark matter and dark energy have been thought of. And dark energy, in a sense, we can see with the acceleration of the universe, or the seeming acceleration, the farther out you go. And we can say, well, there's some kind of force, and we may not know what it is. We could call it the X-force, but we call it dark energy. But something like dark matter, it seems to me that, I think it was in the 1970s, I believe, when people were theorizing that, and some people have said, well, they may be subatomic particles that we don't measure. I think they call it WIMPs. They could be brown dwarfs or machos, which are sort of dark stellar objects. And yet, throughout the last 4 decades, we seem to have come up blank. At what point do you think that you have to sort of say, we've got to come up with something better, or maybe that the mathematics isn't working? I've read, for example, again, I'm a layman, of modified Newtonian dynamics. A few scientists have proposed that as explaining, for example, the reason why the stars at the edge of the galaxy, seem to, that are rotating. What is it? As if there's other objects out there. It could be, at one point, does the observational lack, do we finally say, okay, that simply is not correct, we have to come up with a different hypothesis?
Oh, that's right. And scientists, of course, is not, okay, they have some sort of prejudice, but we know that until we observationally check it, it's not the sure thing. And in that matter, of course, people explore some alternative, certainly, because even that the modifying theory of gravity, many people exploring all possible ways. And in that matter, hypothesis is by far the better explanation than the phenomenon we saw.
Yeah.
And then the phenomenon we saw is clearly observational. Yes, the existence of dark matter is more or less certain at this point. For example, like rotation of the galaxies cannot be explained without the existence of extra matter. Of course, just by that fact may be explained by some modified Newtonian gravity, but we have some all possible other observations, something called Buret clusters. The galaxies clusters collide with each other, and then we can see the distribution of mass by gravitational lensing effect, some Einstein's equation, and the distribution of gas, and that's separating out. So you have to have some matter which is not in a usual form of gas or some usual form of luminous matter. We pretty much know. And despite the fact that we didn't find that matter, for example, whether that is a threat for dark matter hypothesis. And to judge that, you can think about the plane of possible mass and interaction strength the dark matter can have theoretically, consistent with observation. Observation means cosmological observation.
Yeah.
But the region which was probed is minuscule. Simply our technology is not there to cover a lot of parameter space. So you just have to keep looking for. That's the basic theory. Of course, we should not be thinking that that's the only way. We should keep exploring alternative, and people are doing that. And then, but because we have so many observations related with that matter, and explaining that all of them consistently is hard, and that matter hypothesis is by far the best so far. Yeah. And still we are looking for.
What I'm trying to do in this segment is just lay out some basic principles so that in the next segment we talk more directly about ideas about the multiverse. I wondered because, again, as a layman, when I read about or watch videos or hear scientists speaking about the multiverse, they often talk about the fundamental forces of nature and how in a multiverse there could be different universes, different bubble universes, membranes, where the fundamental forces could be different. I'm just wondering, do you think that some of the things that we deal with just in our universe, assuming that there is a multiverse, and in our universe, that our mathematics, our human mathematics, may not be sufficient? And I ask this because, to me, mathematics is a language. It's not reality. Just as we have musical notations for people to read music, just as we have several thousand human languages that are different, could some of the things that we think that we know of be insufficiently expressed by our mathematics as we know it now?
It's possible, but so far we did not hit that.
Yeah.
So that's why, because that's almost essentially only language to do the physical science right now. So we want to see the consequence of that and whether that contradicts observation. And so far not. And so far what we figure out about gravity, space-time, and matter leads us to have certain set of equations, which is not completely unified and complete yet. So people try X-string theory and so on. People try. It's not completely understood yet, but in a limited regime, at least, it works. And if you extrapolate that to the regime, which I've never seen, and then multiverse is an outcome of calculating that equation. And it equation may not apply to that regime. We don't really know, but assuming it applies, and then that's a consequence. And then by studying further consequence, which may connect to the observation, I can probably talk about it later, what kind of possible observational evidence we can get. And by studying that, we can at least see, okay, where to look at and how to falsify this hypothesis. And then we know a couple of candidates to do that. But without thinking that, of course, we don't go anywhere. Well, multiverse, multiple universes, philosophy, yeah, come on, drop it. That's not science. If you do that, if you take that attitude, you don't think about it. And then you won't notice potential thing that they can test, you can falsify, or you can convince yourself. I mean, you have to go there. By extrapolating whatever the mathematical technique we know. Of course, some set of people could do something completely different way of thinking. That's fine. I mean, I don't discourage some people thinking outside. The multiverse is pretty much outside the box, or was outside the box, probably no longer. But the people have to think that way. That's fine. But I don't have a clue beyond mathematics.
How difficult do you think it is within the physics or the science community in general to overturn a paradigm? And I ask this because I remember a couple of years ago, and I just looked this up a few days ago in preparation for this interview. I remember that in 2014, a woman named Laura Mersini-Houghton, a researcher, had come up or shown mathematically that black holes, as we have known or conceived them for the last 40 or so years, can't form as we've thought. And I recently just saw that even Stephen Hawking, whose name is most associated with black holes, said that she was correct, and that what we thought of black holes as having event horizons and all information is lost forever can't be. Are you aware of this woman, Laura Mersini-Houghton?
Yeah, I did not myself detail study and reproduce, so I don't. And as far as I found that particular version of the statement, I don't completely understand or agree at this point.
Okay.
Without really looking into it in detail, but detail enough. But the fact that event horizon, everything forever, the hide and information is lost, I think we were thinking that way in the last 2 decades and so on, and then now we almost start becoming convinced that that's not the case. Yes, that I agree. So I don't know whether Stephen Hawking agreed specific version of her calculation or just the general statement. I agree with the general statement, but not necessarily specific calculation, because I didn't know detail enough that I can make some comment.
Yeah, and let me just end this first segment by talking about a thing that's often floated about, and I'll get more into depth with it when we talk about different possible types of multiverses in the next segment. But, Erwin Schrödinger came up with the thing they call Schrödinger's cat. And this is often when you see little science videos online, or you watch a popular thing like Nova on PBS, or you see in Discover magazine or whatnot. This is all often used to say, well, anything is possible, because if you put a cat in a box with some poison that could be released if an electron decays, or whatever the particular thing is or not, that until you open up the box and look inside, the cat is in both states of death and living, until it decoheres when you open the box and we see it. But even Schrödinger, from what I've known, was using this as sort of a joke example to say that you can't extrapolate from the quantum subatomic level into the classical level, real world level that we live in. The cat is either going to be dead or alive, whether or not you open up the box or not. And subatomic particles are fundamentally different than huge conglomerates of cells and atoms that make up you and I. And so here we have a sort of popular misconception where the scientist was in fact making fun of something, and yet it's used as a buttress for the idea of a multiverse, when originally it was to show how absurd it was. What are your comments on that Schrödinger's cat example, and do you believe that it has been sort of misused in popular culture?
No, I think this Schrödinger cat, I believe that the correct interpretation is that this superposition is called superposition. It's like both possibility of dead and alive both are there. And even macroscopic world, I think it's just there. It's called Everett, the Hugh Everett. That's the person who pioneered this way of thinking. And if you open it, you interact with this system, with the dead or whatever the cat. Okay? The cat is kind of two superposed of the possibility of the living cat and dead cat. Both exist, okay, in parallel world in some sense. And if you interact that, you also become in one world, you see the cat dead. In the other world, you see the cat alive. And you have two you. And the one you never be able to know the other you. That's the current interpretation, or at least it's called something called many worlds interpretation. What's the competitor? The competitor is that in microscopic world, superposition is there. Actually, two possible worlds are both there. That's experimental fact. Okay? If you send in an electron with two slits, you may have one. Electron goes both slits. Without interpreting that way, and then you can't reproduce experiments. So the both worlds are there coexisting in a parallel world. But in microscopic world, it's coexisting. But the macroscopic world, it's not. Then what's the border? Is there any special length scale that suddenly things collapse into one world? Or something human thinking, human observing will collapse the possibility into one, okay? A or B. That's much more radical. Okay? Like a human's observation of human consciousness playing some role. So people thought that that might be the case. Roger Penrose and these people at some point thought that that may be the case. But that's much more radical to me, like if human consciousness playing a special role. It's simply just that things are branching into a lot of probabilistic possibilities. But you are there in many different branches as a different parallel world person, but you don't know the other person because you don't have any way to connect that. But that's what the equation is telling us, because large system impact cannot interfere. That's pretty easy to show it.
Well, I was going. Oh, go ahead. Go ahead.
So that's why I mean it's something like this kind of intuition based is wrong. It's just better to trust the equation. Of course, at some point the equation might be wrong. You have to be open to that possibilities. But for example, Einstein solved Einstein's equation and found that the universe is either expanding or contracting. It can't be true. So he just modified his equation. That modification turned out to be not necessarily wrong, but he modified and then he came up with the wrong cosmological model of static universe. He couldn't believe the equation. And then intuitively that can't be. Universe must have existed forever. And tons of examples like that is Paul Dirac wrote down some relativistic theory of an electron that predicted a particle with the opposite charge with the electron. But of course, people did not have positron back then. People did not know that. So he did not discard that. That was great, his genius. But he tried to identify that as a proton, because proton is the only thing if there's no positive charge particle. But the equation is telling you the same mass particle with opposite charge. And in fact, that was discovered later, positron. So the equation, even if that's contradicting your intuition is based on some your experience, which is very limited. Like you don't sense a special relativistic time delay effect or anything because we are living in so slow moving world. And then any intuition based on that special condition is pretty dangerous to apply. You just first trust the equation and then see what happens. And the multiverse is a consequence of that. The equation we have now. It's not a random guess. That's some misconception people have. It's a random guess, many universes. Yeah, it's great. It's a many, imagination. Not imagination. This is what the equation is telling us under certain assumptions, simple assumptions. And then test whether that consequence is right or not is certainly what scientists have to do.
Okay. Well, I was going to wait until we talk about the multiverse, but since you brought up the double slit experiments, let me end this segment just following up on that. So I would, again, as a layman, I would think that there's a difference between a photon and the conglomeration that I'm speaking to, known as Yasunori Nomura. So if I'm understanding correctly, let's say I ask you a question and you can answer either in the affirmative or the negative. Now, once you make a choice to answer either in the affirmative and I hear you say yes, in another universe, that other Yasunori Nomura would have said no. So we've had a quantum split there.
Yeah.
Now, I would add the thing that I've never gotten with this is now we've got two universes, and forget the fact that this might be happening all over our universe quadrillions of times per second. Where does all that energy and mass for all that extra stuff come from? Because I can imagine, okay, we're going to split the universe and so now we have Yasunori Nomura, the affirmative one and the negative one, and that's twice as much as mass. Not to mention two Earths.
That's sorry. That's not. If you split into the different branch and keep becoming branches, in each branch energy comes out. That's it.
Yeah, but one in the larger multiverse, the fact that there are now two, and then four, and then eight, and then 16, and 32, and six. With every quantum split, there would be infinite Yasunori Nomuras, to the point that all those Yasunori Nomuras at some point would outweigh the single universe that we're living in. So where does all that extra matter come from with this split? You know what I'm saying?
Not extra matter, because it's not in spatially split into two. It's in probability space. So in each branches is a single world. And energy conserved in this branch, energy conserved in that branch, energy conserved in that branch. It just keeps splitting as a possibilities. And you're living in one of them.
Okay,
and you see energy conserved.
So when you use a term like possibility as a layman, this becomes sort of like a ghost. That this is sort of the ghost. So that energy, that matter in that alternate universe is really just hypothetical. Then is that what I'm hearing?
For example, like even microscopic world, we certainly know this is what's happening. Suppose you do the collision of electron positron.
Like in the Large Hadron Collider.
Exactly. In that case, it's not electron positron, but it's some collision of particle. And then the final answer, whether electron positron will just scatter as electron positron, or some particle called mu1 and mu plus, and jet is only probabilistically predicted. That's the result of quantum mechanics. If you repeat it, you can actually test it. And the prediction, it completely agrees. It's just, for single events, you can never be sure what will happen. It's only probabilistically. Okay? So the probability. In any possible outcome, maybe mu, or maybe electron positron, or maybe something called jet, it's all energy conserved, but you don't add up the energy of jet plus mu plus E plus something, right? You don't. Because in each time, it's only one of them, but it's only probabilistic. So you could have been in 90% other universe, or 10% other universe, or 50% other universe, 20% other universe. It's just a probability. In one of the world, it could have been in the other world, it could have been in the other world. It's all energy is conserved and so on. So that's consistent. That's what the equation is saying. No mistake. Just
okay. Well, let's end this segment, and then in the next segment, I want to talk about the different types of hypothesized multiverses by people like Max Tegmark, Brian Greene, and some others. So we'll do that in a moment. I've been speaking with Yasunori Nomura about the idea of multiple universes, or the multiverse, and I tried to lay out some basic questions in the first segment. Now I want to talk a little bit about some of the things that have been hypothesized. If you could first give a little background. Who was the first scientist that maybe came up with the idea that just as the sun wasn't special, just as our solar system wasn't unique, just as our galaxy wasn't unique, that maybe what we think of as a universe, our universe, may not be unique? Who was the first person to come up with the idea of parallel or multiple universes?
It's very hard to really, I don't know, I'm not a historian, so I maybe not be completely able to, because some people, including guests, then of course must have been a long time ago. But when scientifically this theory was made as a theory, is not completely sure, but it's around 80s, was pretty much in current form already. And people like, it's just an example, Andre Linde, and these people, in some form, Stephen Weinberg, and these people already talking. And in certain version related with anthropic world, and some John Barrow and Dipra, they are not in the present form, but many people around that time I don't really know.
Now, the very idea about a multiple universe or multiverse, uh, by its nature, I think, would sort of obviate the idea that the Big Bang, if there was such a thing, was the beginning of everything. Because even if we accept that there was some Big Bang, whether it was caused by membranes colliding or a universe bouncing back in multiple cycles, or the various things that have been posited, certainly there would have to be sort of an eternal multiverse. Is it whatever multiple universes or multiverse that we think of? Is it fair to say that we would say this is something that is eternal, something going back to sort of the steady state, ever eternal universe, except now it's the ever eternal multiverse? So is that correct then?
Well, that is not, we don't know yet.
Yeah.
I also have some idea or some possibilities. I wrote the things, but we don't know yet. And what the multiverse hypothesis is, what we are talking much more, the probable thing is that what we call our universe, we have to define that, by the way, because is there any other universe? What's the edge of the universe?
Yeah.
Suppose you made that question. Suppose you have some edge in the universe. Yeah, there is something outside the universe. If we call that outside, including that outside as a universe, then suddenly there is no edge, right? So we first have to define, when you ask a question, is there any other universe? Then you have to define what you call the universe. Otherwise, if there is edge of the universe, because we can always define outside edge as our universe, then it's our universe. So we have to define the world. And what we call our universe in this context is something we see, like something described by called standard model of particle physics. Say you have a quark and electron as elementary particles with this specific mass. Those regions may not be all. So you may have some completely different region with a different set of elementary particles. Sometimes even the number of spatial dimensions is not 3, but some other thing. So this property could change. But that doesn't mean it can happen. Anything can happen. Totally random, yes. No, we think some basic law, basic principle is common. So far, we think in that quantum mechanics and certain space-time, at least in some region, the space-time picture is a common thing. Yeah. So what we thought as fundamental, some of the things we thought as fundamental may not be fundamental. That's all this is about.
Yeah. Now, let's talk about some of the more popular ideas of a multiple universe or multiverse. It seems to me, from what I've read, most physicists, most cosmologists say that the most likely one would be what we would call beyond the horizon, meaning that if we accept that the Big Bang happened about 14 billion years ago and there was that microsecond of inflationary period where it swelled up 1 billion times larger than it should have, well, we're not going to have horizons that are 14 billion miles, 14 billion light years one way, 14 billion light years the other way, because inflation might have made that 5 trillion light years away. And so once we get past what we can observe, there might still be universes. There might be dark, empty spots, but they would be what we'd call pocket universes.
Yeah.
And so we would still be it would be a multiverse, but it would be more or less a universe where the universes were sort of like galaxies, what we think of the galaxies. Each universe would still be in the same thing, the same reality, but we'd have little islands like that dot the Pacific, that on one island chain we might have the same constants that we have here. But if we go to a far away portion of that universe, we might have totally different cosmological constants. Would you agree that that's probably what most people think is the most likely kind of multiverse?
Me too. But I should add that the theory I propose is that view is in some sense same as a parallel universe we have been talking in quantum mechanics. Okay. I can tell you in what sense these two pictures are even equivalent or same thing. That's my own theory. But the way you described is pretty much correctly one way of viewing. And it's pretty simple, and it's motivated by really like solution of Einstein equation. inflation happens, as you said, it has a huge exponential expansion, so space expands.
Mm-hmm.
Okay? But now you have some phase transition, like boiling water. You have water and then it boils, and bubble and bubble and bubble, right? And usually bubble expands because of phase transition, and they try to complete the phase, bubble expands and evaporate, and then phase transition complete. The water becomes vapor, period, usually.
Yeah.
But even if bubbles start increasing, ambient space in the inflation case is expanding faster.
Yeah.
So the bubble never evaporates. So the bubble goes on. So it's forever the many different bubbles are showing up.
Yeah.
And these different bubbles is a different phase. What different phase means? In particular, string theory string theory predicts that we have small extra dimensions, if you have heard it.
Yeah.
And you have a small extra dimension, like 6-dimensional Calabi-Yau or something. It's like our world is attached with the small dimensions of 6 dimensions. And these 6 dimensions is very complicated object. So you can have a lot of different configuration, like DNA. So you have really like a molecules. Even if fundamental theory is simple, Schrödinger equation, the solution takes a lot of different form, right? There's DNA, RNA, and so on, a lot of different configuration. So the shape and size of extra dimension can be a lot of different, bubble by bubble, the different shape of extra dimension. That corresponds to a 4 dimension, corresponds to different force, different elementary particle, and so on. So we look like elementary particles are different in different regions because configuration of this small extra dimension is different. And that's dynamically happening by bubble creation, and eternally going on, a lot of different universe. And then a lot of different place has different properties, like different dark energy. Dark energy is the energy of the vacuum. So different energy, different vacuum energy, different places, different conditions. And the region you will show up is very special condition is needed. It's clear that if the vacuum energy is different from our own world, and you can show that you won't arrive because even galaxy doesn't form. So minute you form and you look around your own universe, it looks very special condition, very special parameter, very special structure like electron and so on. But that's not the mystery because you have many different universe with different parameters. It's the same like many different planets has different conditions, but you're not there and you're only in the Earth. And if you look around, why this is so beautiful, trees and lake and so on, and so much finely tuned. The distance from sun is so miraculous that somebody must cook up this. I mean, some creator must cook up this. No, because there are many planets. And only if the condition is right, you're there, and you look around, oh God, this is just completely miraculous. The same thing seems to be happening in the universe.
Now, because this would be have somehow come about from the singular Big Bang that would have made not just a universe but the multiverse, presumably, would that mean that, let's say hypothetically, we wouldn't have to go tunneling into some other kind of quantum universe? We could, if we say could build a vessel that could go 1 billion times or 1 trillion times faster than light, we could then somehow hop from island universe to island universe just by traveling through space-time in this kind of multiverse. Is that correct? And as in the old conception of the universe, presumably maybe if this is a closed and finite multiverse, no matter how, it might be an infinite universe, but if it's closed, we could then travel and somehow come back into our universe. Is that correct?
That's not trivial. For example, this is really, and I will certainly have to tell you that in what sense this version of the universe is the same as previous version of a parallel universe. And first of all, let me just start from there. It's not directly, may not be directly answering your questions.
Yeah.
But for example, if this is far away, much farther away from the kind of event horizon is, then in what sense this universe exists? Because you can never check it, right?
Yeah.
If it's far away.
Yeah.
Really far away. If not, you may be able to go. I will come back to that later. But if it's really far away, outside the horizon, you will not be able to go. In what sense this universe exists? But I said that this bubble universe is a phase transition, like a bubble creation process, and then immediately becoming far away, and you can never even go because because it's exponentially expanding. It's faster than speed of light, so you can never be able to catch up.
Yeah.
Okay? So, but it just, this process is quantum mechanical process, because it's a tunneling process, by the way, tunneling to different universe. So that's exactly the same as quantum mechanical process in a sense that the electron-positron scattering, it becomes electron or a jet or muon or some other particle. That's quantum mechanical process. It lives in a different probability space in some sense. It's the same like this bubble nucleation is quantum mechanical. So probabilistically, you could become inside the bubble A, or you could become inside bubble B. It could become this universe, or you could be inside that universe. You could be at that universe quantum mechanically.
Yeah.
So in that sense, this picture is equivalent with the previous one. Okay, it's all quantum mechanical probability. You could have been in any other locations or any other bubble nucleation probabilistically. So it's the same thing. Now your question, I mean, in one of the universe, suppose you hit into one of the bubble, can you explore other bubble and then come back? Usually no.
No.
But you still can see that this is a reason. For example, suppose you may think that the time is like this slice. This is a t equals 0, it's a big bang.
Yeah.
T equals 1, it's a big bang.
Yeah.
T equals 2, it's a big bang. T equals 3, it's a big bang. T equals 3 and T equals 4, T equals 5. This is time 0, time 1,
Yeah.
time 2, time 3,
Right.
and time 4.
Yeah.
Is it clear?
Yeah.
Suppose you think, you draw that figure.
Yeah.
And then this time 0 is a big bang.
Yeah.
But in this bubble nucleation, inside the bubble, people usually say it's infinite universe. Have you heard? Yes. The bubble universe is infinitely large universe. But from outside, if bubble formed and then become bigger as the time goes on, how come these two pictures are consistent? Right? It's a bubble forms, it's a finite size, and it increases. But if you're living inside, you feel that universe to be infinitely large.
Yeah.
And these two are consistent because the concept of time is relative. If you look at the bubble from exterior, let's call this the time axis, vertical.
Yeah.
And this is a spatial. And then the bubble wall is like this triangle.
Yeah.
Then if you just cut this thing at some fixed time, and the size is like this much, and another time the size is bigger,
Yeah.
and another time size is even bigger, right? Because I'm just drawing them.
Yeah.
But for the time, for interior observer, the time 0 is this exactly this line. And time 1 is next line. Time 2 is the next line. Time 3 is next line. So even time 0 of the universe is infinite. Because to see what is the size of the universe, you have to slice in equal time and then measure the volume, right?
Yeah.
And this equal time is different for different observers.
Now,
So that means that this inside this triangle is our universe, and then outside is the other parent universe. That means that from interior observer's point of view, this is before time 0. So in other words, it's a past.
Yeah.
In this diagram, the speed of light is 45 degrees.
Yeah.
So you can't move faster than the speed of light means that you cannot go beyond 45 degrees. You can do is only this. Up in time. The time is vertical axis. The horizontal axis. So you can't go to the parent universe because that's kind of past.
Okay.
That's how things work.
Now let me just one of the reasons that people sometimes talk about multiverse too is to explain why our universe is conducive to at least human life as we know it. And the three classic explanations have been, well, there's a designer, there's a god, there's a deity, there's a thing. The other explanation was, well, there's an infinite, an eternal cosmos, and if something is infinite and eternal, given enough time, something will happen. And the universe, even if it started out in a different state, at this point in time, it is conducive to human life as we know it. In this idea of the multiverse, though, because there is an infinite amount of bubbling universes coming up, it's just bound to happen at least once, if not infinitely. And there may be, so it's almost like Nietzsche's idea of eternal recurrence. Sooner or later, there's going to be a universe that's conducive to life as human beings know it, and then it's going to happen again and again and again. We may never be able to get to that place, but there will still be a Yasunori Nomura X amount of cosmoses away, talking to a Dan Schneider X amount of cosmoses away. That's just what infinity is. So that's that kind of universe. Let's talk about the quantum, or that kind of multiverse. Let's talk about what we had talked about, the quantum kind of multiverse, where we have quantum splits anytime there's, well, uh, in the quantum universe, does it take an active decision by a decision maker to split it, or is it just probabilistic that something could go two ways that it'll split? But what happens if there's some? Yeah. So, but what happens if there could be 87 potential outcomes? Does that mean that there's 87 potential, universes that could come from one single split?
Yeah, in fact, it's not discrete number. You can calculate the probability. That's continuous number even. Yeah. Like A, probability A and 1 minus A. If you have two possible outcomes, you have three possible outcomes, A, B, and C, with A plus B plus C being 1 or 100%. Yeah. And you can even calculate it. So that's what particle physicists are calculating at the microscopic level. If you scatter these things, what's the probability of going the final state, the distribution? And the same thing applies for bubble creation. That's also a quantum mechanical process. What is the probability of having universe A? What is the probability of having universe B? What is the probability of having universe C? And continuously, these things are splitting into a continuum number of possibilities. So nothing, no intervention from observation of humans' consciousness. No, you just solve the equation, and in probability space, things are splitting. That's the solution of the equation.
So universes would then branch off probabilistically. It wouldn't be, that would be fundamentally different between the first type that we're talking about, where we have the Big Bang and things are just bubbling like boiling water. The bubble. These are not things bubbling up from quantum reality or whatever we want to call it itself. These are things that are probabilistically happening at points in time. So the fundamental difference would be what then? To explain that, what is the difference?
People thought it's a fundamentally different, but what I proposed was it's the same thing, because this even bubble nucleation is a quantum process, so it's the same thing. It's just a big version of this particle experiment.
Okay.
The big version. That's because it's a probabilistically sometimes A, sometimes A here, sometimes A there, sometimes B there, sometimes C bubble there, sometimes D bubble there, and that's a probability because it's a quantum process. This bubble nucleation is quantum tonic process. It's exactly the same as scattering experiment. It's just things are happening in probabilistic world. That's it.
Yeah. Now, so if we were to say bring both of these concepts of a multiverse down to, say, a two-dimensional, say a sheet of paper, let's just use a thing, all of the quantum many worlds hypothesis kind of multiverse, if that was on one sheet of paper, and then you have the sort of bubbling over the horizon multiverse on one sheet of paper, there's also the kind of idea that you would have universes sort of what we call a membrane idea that some people have proposed in the last 20 or so years, where you would have, say, it would be, let's say, like a sheet of paper, like a ream of 500 sheets of paper, although these would be infinite universes that are sort of just floating in some kind of, I don't know what, and every so often some of these sheets, these membranes, bang into each other. And when they bang into each other, they somehow, some people have said this is what the Big Bang was. It was the banging together of these membranes of reality that somehow created our cosmos. Do you have any truck? I mean, could you sort of explain that? And do you think that's as likely or less likely than these other two types that we've just spoken of?
That kind of phenomenon could happen in, at least even in this version of many world type picture. And that kind of phenomenon could happen in one branch, right? It's not mutually contradictory concept, because this is a probabilistically many things happen in some universe, just bubble form. In some universe bubble with 5-dimensional forms, some universe bubble of 10-dimensional forms, some branches you may have some bubble of the 8-dimensional forms, and in which you may have 5-dimensional, 4-dimensional world colliding. That's nothing wrong. So it's certainly not mutually inconsistent phenomena. But whether our own bubble or our own universe, the past, is a collision or bubble new creation is a well-defined question. Right? It's not about somewhere in the branch. Our own universe, at least the branch you and me are talking right now. And the past of that branch is, immediate past of that branch is a bubble new creation, as I was talking, or colliding of the 3 plus 1 dimensional, lower dimensional object is a well-defined question. And my just personal sense, based on some observational thing, is that bubble new creation is more likely, but exploring alternatives certainly at the very least is worthwhile endeavor.
Now,
and so we don't really know.
I want to bring up 2 other types of multiverses in a moment, but they're far more speculative in my lay opinion than the first 3 that we've talked about. How could we, let's talk about the first 3 that we mentioned, the membrane type, the bubbling multiverses or universes within a multiverse, and then the sort of probabilistic many worlds interpretation.
I said the last 2 are equivalent, and the first one is just different. It's not necessarily multiverse. It may be happening in one of the branches.
Yeah. How can we observationally test this? I've read that some people propose that of the four necessary forces that we have in this cosmos, the weak and strong nuclear forces, electromagnetism and gravity, that electromagnetism and the strong and weak forces are inherent to just our known universe, whereas gravity may be the force that's across the multiverse. And the reason that it's so much weaker is because it is spread out across all of these vast cosmoses within the multiverse, and that perhaps that I've read that some people think that some of the things like dark energy could be some forms of gravity leaking in or something from other cosmoses nearby. Am I interpreting that correctly, or how could we observationally?
I don't know. I don't think. One of the ideas that was talked already was that we may be living in subspace.
Yeah.
This is a 3-dimensional actually. I'm just writing at a 2-dimensional seat, but actually this is 3 dimensions.
Yeah.
It may have some other space.
Right. Yeah.
And then gravity may look weak because it just spreads out. Mm-hmm. But this is not the multiverse thing. This is like we are called something we are living in brain world.
Okay.
And then weakness of gravity may be because there are some other, I said like 6 compact dimension is there in string theory. This dimension may be large. Mm-hmm. That may be the reason why gravity is weak. So that's like separate idea with the multiverse. We can be combined. It's some of the multiverse branch that may be happening.
And let me just clarify, because a lot of times in popular culture, when people are thinking of what we would call, what we've been speaking of about multiple universes, they'll say it's in another dimension. Well, what they're really meaning is another universe, because the dimension is, you have breadth, width, height, and then you would have dimension X, dimension Y, dimension, whatever, something pointing. It's, if you had a pencil and you could go in this direction, it would be another direction. When people just confuse and conflate the word dimension to mean a universe. Now, I had said that there were 2 other universes that and there are probably a couple of dozen, and I don't want to get into all of them because some of them are so abstruse that you'd have to take an hour to probably explain them. But the 2 that I did want to speak about that I did find interesting, but I think are probably, just as a layman, far less likely than the 3 we talked about, is there's, I guess, what was called the holographic idea of the universe, that somehow we are living inside maybe a super black hole, that our cosmos formed inside of a black hole, and that we're somehow 3-dimensional shadows of some reality on the interior of a black hole that's in higher dimensions. Or at least that's the way I, as a layman, have interpreted reading this. Can you explain what this idea of?
Yeah, I think first of all, the word holography is used much more general than that. namely, suppose we live in D-dimensional space-time.
Yeah.
Our case is a 3 plus 1 plus some tiny 6 dimensions. But say any D-dimensional space-time.
Yeah.
And there is a theoretical way to describe that D-dimensional gravitational space-time in terms of D minus 1 dimensional theory. And people start seeing tons of evidence for that. That's just a property of gravity. Has nothing to do with specifically our world is inside a black hole, any of those. This is a probably property of gravitational theory. There are equivalent description in terms of one dimension less.
So that would mean that we're describing it by using a metaphor of bringing it down to one dimension. Like in Edward Abbott's famous book Flatland, he talks about a square living on a two-dimensional surface, and then a sphere comes and tries to explain to him the third dimension. So we're using that as a metaphor, D minus 1. Is that correct?
Or for example, like if you have D minus 1 dimensional space,
yeah,
but each point of that space has a color, red or blue or something.
Yeah.
Okay? Different colors and so on. Or maybe even grayscale, like white to black. Then you can describe this as 2 plus 1 dimensional space plus 1 dimensional color space from white to black.
Okay.
You can rewrite everything as like a 3-dimensional thing, right? Because just dimension is just one label, X, Y, Z, right?
Yeah.
And if Z looks like color, then like 2-dimensional space with color is the same as a 3-dimensional space without color.
Mm-hmm.
That kind of rewriting of the theory is possible. Okay. That's in a theory of the gravity, you can just always do in the lower dimensional description.
All right. Now, the final one that I guess I want to talk about or throw out there, and then I just want to ask a few other questions in a more general term, is people have the idea of a simulated universe, which would be, I call sort of the techno version of the tortoise is standing on top of the tortoise shell on top of the tortoise shell, i.e. that we are living inside of a computer simulation. And my argument all is, well, that doesn't really solve anything. That's like, just pushing God back farther and farther from reality. Because if we're in a simulation, well, then the creatures or the beings that develop the simulation could themselves be in a simulation, who could then themselves in a simulation, to infinity minus 1. But there would still have to be some underlying reality. But yet I've read, some people who think that they'd say, well, when we get very down to the very fine grains of the quantum world, even if there's some smaller particles and quarks or strings that has been posited, that it looks very much like what we think of the binary 0101 that we use for our computers. Do you think that that's just fanciful, or that that's just, a nice, story science fiction wise? But, there would have to be at some level some base reality, because simulation, we could simulate universes going on, but there would have to be some base reality. Do you have any favorite?
I think this is something I don't kind of understand. Suppose this simulation is based on certain rule. Something we call physical principle, physical law.
Yeah.
We could say that this is a simulation of somebody, or we could say it's reality, but identical consequence, right? Because if the simulation is perfectly obeying that law, we say that's the physical world or somebody's simulation. It doesn't make any difference. It's just a philosophy. It's philosophically quite different, but it may be just this rule will determine what will happen in next. In that sense, it's completely same. So, for example, like the progress of science, in my opinion, happened like accelerated at beginning or late 19th century or beginning of 20th century, because we really stopped asking these kind of question. I think, for example, it's the following: like people ask why this is the case or something, right? Why A is B?
Yeah.
This makes sense. The question like is that really like simulation? Why A is B, or why it's simulated? Why is it reality? Why A is B? But then you may answer, oh, because C is D. But then you can ask, why C is D?
Yeah.
And then, oh, because E is F. Why is F?
Yeah.
Or because it's G is H. It doesn't make any sense, because so we focus our goal on explaining the same phenomenon by smaller number of assumptions, then we call that theory as a better theory.
Yeah.
For example, this the theory of planets. Of course, Newton's way is much better than Ptolemy, because Ptolemy you have to have a lot of rules, but it's sufficiently complicated rule you can explain the future. But Newton's rule is much simpler. It's just simply R square laws, and then you put three principles, then you can calculate everything. That's a better theory. So we keep reducing number of axioms. So then if the number of axioms is the same, then it's the same description. Whether you view that as a reality, or whether you fantasize that that's a simulation that somebody has got, it's identical consequence with the identical number of assumptions. Then it's the same theory. And if one has a smaller number of assumptions, that's a better theory. We should adopt that. If the consequence is the same and one has a smaller assumption, then that's better theory. We focus the goal of science to be that part. I think that's important. Otherwise, it can be asking something you can never answer, or something completely outside the realm of science.
Yeah, because science can only ask how. It can't really ask why. So there may be some fundaments of, we can call it the universe, the multiverse, reality, existence, that just are. And, you know, there's no, we can't, we get to that final thing and we can say, well, this, we get back to a first cause or first principles, and there's no, that's just the way it is. And how it came about or why it came out is something beyond science. But human beings.
In other words, we define answering to why question.
Yeah.
We define that as reducing the number of axioms.
Yeah.
That's our definition of answering to why question.
And that's deeply unsatisfying for human beings, since we are primates that want to hold things and taste and use our primary senses and stimulate our brains as to why does this taste good when that other fruit doesn't taste good? Why do we do this? And so I think that's at the root of it. Let me just ask you then, you had said that you have come up with your own theory, and I assume at some point you're probably going to write a book or something about it. You said you sort of meld the many worlds interpretation with the bubbling universe. What do you call your theory, and how is it different than either of those two, and how does it meld some of those ideas?
Well, I call it multiverse equal quantum many worlds.
Okay.
Just not sufficiently cool name, but
okay.
that's the and its difference is that if in this, for example, many worlds is people not talking about these possibilities. Okay, but just many worlds. That's my message. Like usual bubbling eternally inflating universe, you think that you can go, this space exists forever. Far away, that really literally exists. But that poses a problem with infinity, because it is, as you notice, and the things happening infinitely many times and infinitely stretching, so you have infinite space. And you can't talk about even probability, it's just called measure problem. It's a huge infinite space, and everything happens infinitely many times. Suppose you do some experiment. The result of A happens infinitely many times somewhere in this infinite multiverse, and B happens infinitely many times somewhere in the multiverse. What's the relative probability? Is infinity over infinity? You can't define it. That's not what happens. Actual space-time is finite extent. Beyond the horizon, it doesn't exist, because you can never go there. But on the other hand, probabilistically, so your space is only within the horizon you can reach. But probabilistically, you can live in different inside the horizon configuration. You have a different configuration, so you can define probability and so on. So the way you view what the space and time is quite different. But if you focus on one single observer, the picture looks quite similar.
Now let me ask this, because when I was a kid going to school, I was taught that science, to be science, that theories are accepted, but they're only always ever just contingently accepted. They can be falsified. Tell me how your particular theory or any of these multiverse theories could be proven definitively false, that we may not be able to ever definitively prove that these are, But in order to really be science, someone would have to say, Yasunori, I'm going to show you why you're wrong, and this is why. Whether it's an equation, whether it's something observational, how can it be falsified?
Definitely, of course. First of all, falsifiability in a narrow sense is not necessarily equivalent with the criterion of science, in my opinion. Because, for example, how you can falsify, for example, can you prove the existence of dinosaurs? Yes, more or less, right? I mean, the evidence is massive, but nobody really literally went back.
Yeah.
And if you could start talking the possibility that, oh, maybe UFO came at some point and then they made up all these things, and how you could disprove it.
Yeah.
You just say that, it's crazy. I mean, it's just, right? But on the other hand, how you disprove it. And so
how could we now prove that Abraham Lincoln was killed by John Wilkes Booth? We just have the written accounts. We don't have the newsreels or the footage of it.
Yeah. So in some sense, always we have this Bayesian way of thinking, like what's the most natural explanation, the smallest number of hypotheses, and so on. Right? That's from the beginning. So now the multiples, and I have a different level, a lot of different possible experimental thing I can point to, but one probably simple thing. Suppose this bubble version of the universe, multiverse, is right, okay? Including my case that is equivalent with many worlds. We are living in one of the bubbles. One possible positive experimental signatures people are talking is if you have a nearby different universe and universe collide, then you might see the signatures of that. If that happens, that's great. If you're lucky, and if you see signatures in the sky or cosmic microwave background, and then we probably see the collision of the different universe in the sky, then that's convincing. But that you have to be lucky. The other possibility I was talking with, say, Alan Guth, the part of the information theory, is if this bubble version is correct, as I said, equal time as viewed from inferior person is this type of, this is time 0, this is time 1, this is time 2, and time 3. So this bubble universe looks negatively curved. That's the consequence. You just solve the equation. This bubble universe looks negatively curved. What that means? If you have a flat seat, then if you draw a triangle, then the three angles adds up to 180 degrees, as is well known.
Yeah.
But if the surface is positively curved, like surface of the Earth or surface of the sphere, then if you draw a triangle, meaning that the shortest distance line, then the shape is like this, right? It's just slightly swollen. And therefore, the angle, three angle adds up to bigger than 180 degrees.
Yeah.
That's called positively curved. And if it's a negatively curved, it's a similar surface. If you draw a triangle, the addition of three angles is smaller than 180. And the prediction of this bubble universe is that interior of the bubble looks like universe with negatively curved. So if you have a triangle made by light rays, there is shining light, that's straight line, shining light, and shining light. And then addition of the three angles must be smaller than 180. That's the prediction. But the catch is that you cannot predict how small from 180. So it could be 179.9999999.
Yeah.
And the current experimental result is consistent with 180. And plus minus 1 degree.
So the universe is flat then?
Yes, purely flat. So that does not kill this multiple thing because it's flat. It may look flat, like 179.9999999 looks experimentally flat, but it's definitely negative. So in the future, if you see the curvature which is positive, 180.01 plus minus 0005, then it will definitely exclude this version of the multiverse of the bubble universe. And this is a place where the experiment will become 2 orders of magnitude better. This measurement of the curvature in our own universe become 2 orders of magnitude better in the next, 20, 30 years. So, and there, if you see the sign of positive curvature unambiguously, then forget about at least this version of the multiverse of bubble nucleation. Completely forget. It's hyper-falsifiable. That's much more falsifiable, for example, than some other theory in particle physics called supersymmetry, for example. Because supersymmetry people are searching for in the collider, spending a lot of money, and I think it's worthwhile doing that. But if you don't see it, you could say, oh, the supersymmetric particle may be slightly heavier, and maybe slightly beyond beyond our power, our reach of our collider, so let's build the next one. And if you don't find the supersymmetry there, maybe slightly heavier, you can always. Here, no. If you see the positive curvature, end of the story.
All right, well, let's end this segment. In the final segment, I want to give you a few minutes to just wrap up some of your ideas, and we'll talk about what you're going to be doing in your own research in the coming years, and we'll do that in a moment. I have been speaking for the last hour or so with Yasunori Nomura. He is a theoretical physicist. We've been talking about different types of multiverses, whether it can be proved or falsified, and he was just explaining a bit of his ideas about the multiverse. So let me just talk in the near term and the long term. What are you going to be refining your theory and putting out a book in the next few years? And in your lifetime, do you think that there will be proof one way or the other about the multiverse?
Okay. I'm certainly exploring the further aspect of this theory. And one of the things is, like, as you already mentioned, it's holography. This is the idea that the whole thing I was talking can be formulated in one less dimension or more, not less redundant way. Okay? That kind of new description is speculated or postulated, and then but nobody knows explicitly how to do in the cosmological setup. That's one of the things I'm focusing on a much shorter time scale. And about this multiverse, I already wrote a couple of public blog and so on, and I'm currently writing some public article. Book I'm not completely sure, but at some point I have enough material, and then I might certainly do it. And long term, I'm really thinking that this quantum gravitational multiverse is related with all what's the probability or what the meaning that you observe, namely all the question of quantum mechanics, all question of what is the meaning that you measure or you become reality and so on. And some part may not be scientific question, but the people struggling, there are certain aspects that you should feel pretty weird. You may just have to accept. But that's something I'm thinking in a longer time scale, whether I can make something clear and not in a philosophical sense, but have some better understanding about that nature of being probabilistic, something we can predict the probabilistic. I mean, what that really means, and that's my longer term.
Okay, well, anyone who has enjoyed this conversation with Yasunori Nomura, I will be linking to his webpage at UC Berkeley. Anyone who has enjoyed it can contact him there. And I just want to thank you for spending an hour or so talking to me about the multiverse and trying to help people understand it a little bit better.
Thank you.